아,
Good morning, everyone. Can you hear my voice? Yep, okay. Then I will start the practice session 3. Today we will cover the basic concepts of the PyTorch framework using the
그래도
tensor operation.
날씨가 많이 시원해진 것 같은데요. 네.
Is there someone who didn't mute the... Okay, I will keep going. And then we will implement the simple logistic regression and multinomial logistic regression with this PyTorch. And then finally, we will implement the simple linear model and multilayer perceptron in this class. So if you have any questions, feel free to ask. And for additional questions, please use the KRMS Q&A session. So firstly, the PyTorch is a very popular library for building the AI models. And especially for the deep learning, we will use it through the IPYMB notebook in this class. And the NumPy is also a library that helps us to work with numbers of arrays. And it is widely used in AI to handle the data before we turn it into a format that PyTorch can work with. Firstly, we will check that what kind of GPU we can use. So here I will okay. In this case, we will use the T4 in the practice session, and here we can visualize the current GPU usage in your server, and then we can set the GPU number. So here we set it as the 0, and then we will load all the packages we will use in this session. So we will use the PyTorch and NumPy. And after that, we will check what kind of the version. So this helps us to confirm the PyTorch is correctly installed and tell us what version we are going to use. And knowing the version is very important because sometimes different versions of the software has different features. So from now on, we will show the examples of the same operation with the identical grammar and same operation with different grammar and different operation with the same grammar between the PyTorch and the NumPy because there is a little bit different points between them. So NumPy arrays are the array of numbers that we can work with in Python. And they are very easy for doing the math operation, but they can't be used directly with the PyTorch models. But PyTorch tensors, they are like also similar like NumPy arrays, but they have extra features. The most important thing is that tensors can be processed on the GPU, which makes us faster to work within AI models, and we often convert NumPy arrays to tensors, so PyTorch can be used on the GPU. So here we make the examples of the NumPy array and the tensors. At the same time, in this point, they have the same shape, and let me see the same operation with the identical grammar. So when we want to check the shape of the tensor, we can use the NumPy array shape, or also in the PyTorch tensor, we can use the shape or the size function. They give us the same result. So here we have the 4 elements. So it returns us the torch size as 4. And this is the example of the same operation with different grammar. When we try to concatenate the two tensors, NumPy array use the NumPy concatenate, but PyTorch use the torch cat. So you should be aware that they use the different grammar. However, they are added in the axis 0, and the torch also concatenated in the dimension 0. They give the same result as like this. And this example is shows the reshaping and the view functions of the NumPy and the torch. Reshape is the tensor reshaping is like we can change how the data is organized, like turning a list into a table that has the row and columns, or just back into a list. And the repeat function, this led us to duplicate the elements in a list or tensor. And in this example, we first create the 3x1 shape of the tensor. And then we can repeat each element twice. Like here, 1, 2, 3, it has 3 elements and we repeat it. And also tensor has the 1, 2, 3, and we can repeat it. But we should aware that it gives us the different result because the NumPy repeat, it just duplicate this 1 as 2 times in one side, but PyTorch duplicates just concatenated the tensor 1 to 3 in the same dimension. And also using the view function, we can reshape the PyTorch tensor in this like 3x2 shape of the matrix. And also this function, the last one show flatten the tensors 3.3x2 as the 1x6. And also this gives a similar manipulation operation like using the stack and repeat. In this example, the input X is the torch tensor which has 3 elements, and we repeated it as 4. And then, so we can see that each element 1, 2, 3 is duplicated in 4 times. And when we use the PyTorch stack function, it stacks the input X by the different stacking in the rows. And now, in this section, we will learn how to utilize the GPU in PyTorch. And we should check the GPU availability. So PyTorch can use the GPU to speed up the calculation or the computation of the tensors, but this function can check if the GPU is available on our machines. So when we print the CUDA is available, it says it is true. And now I will make the random arrays like this. A is the torch ones with 3. This means that it creates a tensor with 3 elements that all of them set as 1. And torch random 150 and 3, it makes the random number of the shape tensor, which has the 100 rows and 50 columns and 3 layers. So random tensors are often using when we initialize the data for a model. And it says the A and B all of them are on the device of the CPU. But now we want to change the device to the GPU. So we unload A and B to the GPU like this. So now we can check the device is changed to the CUDA 0 because we set the device number as 0. It says the CUDA 0. And now we can add the A and B. And now we can check the device of the C is on the GPU because we made the A and B set on the GPU. But when we change to back into the CPU, we can use the C.2 CPU, and we can see that the device is changed into the CPU. When we see this operation, we add the tensor A to the tensor B, and this operation happens like element-wisely, which means that each element of the A is added to the B. Next is the Autograd module. The Python Autograd packages provides the automatic differentiation for all operations on tensor. And the PyTorch tensor is the central class of the package. And when we set the requires grad option as true, it starts to track all operation on we had the computation before. When we finish our computation, we can call the backward function, and all of the gradients computed automatically. So we don't need to calculate it by ourselves. And the gradient for this tensor will be accumulated into the grad attribute. So here at the start, let me see the example. For example, the input X is the 2x2 matrix with all the elements is set with the 1, and we set the requires grad option as true. And the next we add the element-wisely 2 to the X. So now the Y is the 2x2 matrix. It's the old element is as 3. Is there someone who didn't use the mic? Okay, I will keep going. And G is the multiplication of the y square and 3. So now the value is changed at 27, and still the shape of the tensor is 2x2. And finally, the output is the mean value of the G. So all of them has 72 value, and elements are 4, so the mean value is the 27. So now we can calculate, we can try the gradient. So here, you can see that the output is the mean value of the G, and so the round output out of the round C is like this. And also, using the chain rule, we can set the round out of the round Y like this, and the round C out of the round Y is the 6 multiplication of the 6 and Y. So it gives this result 4.5. And finally, the round out of the round X can be decomposed as like this using the chain rule. So the final value should be 4.5, and we can check all of this process like this: C grad and Y grad. Oh, I didn't set the retain grad. And then we can check the final value is 4.5 as we calculated before. And to prevent this tracking history that we should use the memory, we can also wrap the code block with the torch no grad function. When we try to inference the trained model, so that we don't need the gradient calculation anymore, we can set the torch no grad like this example. Then torch doesn't generate computational graph for backpropagation. Therefore, it is much faster in computation. So even though it has the forward pass just same as like just before previous example, but it is blocked with the torch no grad. And the output value is same as the previous example, but when you try to backward the output, it gives us the error because we use the torch no grad. And this picture is the whole process of how the parameters of model are updated through the forward pass and backward pass. So from now on, we will use the predefined modules and then module in PyTorch. We will practice how to train and test the models. So firstly, we set the input X like two by three shape matrix. And this function, and then linear creates the linear function with an input size of 3 and output size of 1. Linear function is simply the equation that y equal wx plus b. And here the w is the weight matrix and b is the bias. So when we give the input x when we pass the input x into the linear function, we can see the output like this. The input shape was the 2 by 3, and the output dimension we set it as 1. So the result shape is the 2 by 1. And after that, we sum all of the elements in the y. So the final answer is like this. And there are a lot of modules in PyTorch, like convolution or RNN and LSTM or transformer. So you can use all of the module. So how can we change a customized model for the neural network? This part defines a customized neural network model using the PyTorch NN module. So firstly, we defined 2 fully connected layers and the ReLU activation function. The first layer transforms the input from the input side and output as hidden sides. And after the ReLU activation layer, the dimension doesn't change. And finally, the third layer takes the hidden layer's output and produces the output dimension. So usually the output dimension is same as the number of the classification labels So if we have the 10 classes in the data set, the output dimension should be 10. The activation function, here we used it as the ReLU function. This make the nonlinearity for deep neural networks. So the deep neural networks can approximate the complex functions. And there are more activation functions in NN module, like sigmoid or ReLU or leaky ReLU and hypertangent. You can use all of them. And here we will see how can we apply these packages for the multi-class classification task. So we will use the MNIST dataset, which is the handwritten digits from 0 to 9. And it has training set of 60,000 examples and test set of 10,000 examples. Because we have 10 classes, 0 to 9, so this problem it is like can be interpreted as multinomial logistic regression, which means the multi-class classification with 10 classes. So we will and we will use the softmax function to handle the multiple class output with cross entropy loss function. So all of the process will be continued like this. So firstly, we will load the packages. And then we will install the, and then we will load the data set from using the packages, like the Torch Vision gives the data set packages. So the train set and the test set for the inference. And then we load the data set on the data loader. We set the batch size at 128, so each mini batch has the 128 examples, and we can mix the order of the samples by setting the shuffle option as true. But we don't usually mix the order of the samples when we try to test. So the test loader has the shuffle option as false. And now we can define the model. When we define the model, we use the fully connected layer because this is very simple model. So we will just use the linear model. And as you know, the input image is the 28 by 28 pixels. And the MNIST dataset has the 10 classes. So when we set the input size, we set it as 784, which is the multiplication of the 28 and 28, and the output size should be 10. And now we can see the model structure like this, which means the fully connected layer, that input size is 784 and output size is 10. And to use the GPU, we upload the model to CUDA. And also, we have to define the optimizer. Optimizer is the option to find the best solution, and PyTorch has variable optimizers. And in this time, we will use the SGD with momentum 0.9. As you know, the momentum has to find the best solution that fits for the given data set. In this case, we used the MNIST data set. So we set the optimizer as the SGD, but you can try other optimizers like Adam optimizers or SGD without the momentum. So now, after we define all the models and optimizer, we set the loss function. So in this example, we will use the cross entropy loss function. So this for loop is for the training the model. When we try the training the model, this loop runs through the entire data set multiple times, and each pass through the data set is called an epoch. So here we set the epoch as 10. And in the forward, and each of the epoch, it has several mini batch for loop, and we remember that we set the batch size at 128. So each loop has the 128 samples. And in this forward pass, the model makes the prediction of the input data images, and the result is stored in the output. Here we reshape the input data as 784 because we set the linear function's input dimension as 784. And after we calculate the output, we calculate the loss using the cross entropy. And then after we check the loss of the prediction, loss between the predictions and the real labels, we try the backward process. This is the backward and optimizing process part. Firstly, we set the optimizer as 0 grad, and then the loss backward computes the gradients of the loss with respect to the model's parameters. And then the optimizer step updates the model's parameter using these gradients. So after all of these 100 steps, the code prints the current epoch and step and losses as the step goes by. So let's try it. So we can see the loss is decreasing, but it is still unstable. And it might be that the model is too simple to train the MNIST data set. So finally, the training is done. And the last loss is 0.1469. And after we train the model, we should test the model. So here we will try the inference. So during the testing, we don't need to compute the gradients anymore. So this is the reason why we set the torch no grad in this block. So this saves the memory and speeds up the evaluation. And the model's prediction are compared to the actual labels. And we count how many predictions were correct in each predictions. And the accuracy is then calculated as the percentage of the correct predictions out of the total number of test images. So here after we pass the input images and get the output, and we get the max digits out of the 10. So we get the highest digits from the 10 classes. And after that, we check if the predictions and the labels, actual labels are same. And we count how many predictions are correct. And this is how we calculate the accuracy. Let's try it. And it says that the accuracy is 92%. And the previous model used the multinomial logistic regression with the one linear layer. But when we let's try to the multi-layer perceptron, that the neural network with several hidden layers. So here, the neural network has the 3 linear layers and use the sigmoid as the activation function. And you can change the structure of this model as you want. And now we generate the model like the same as the previous example. The input size should be 784, and we will set the hidden size as 20. This hidden size is the hyperparameter, so you can change the size as you want. And in this case, we set it as 20. After we unload the model to the GPU again, we will calculate the loss with the cross entropy loss. And then we will use the optimizer with SGD. And you can check the model accuracy using another optimizer or change the structure of the model. So this is the training step again. So we set the images, we change the images shape like this and upload the X and Y to the GPU. We compute the forward pass like by giving the input image into the model and get the prediction. And then we calculate the loss, cross entropy loss between the predictions and actual labels. And we calculate automatic gradient using the backward and update the model parameters. And after that, we print the loss and the step. So let's try it. And here we can check the loss is decreasing as the step goes by. Started from the 2 and it is almost 0.17. And training is finished. And now we can inference the model, the trained model. So again, we set the torch node red because we don't need to compute the gradients anymore. So this is this variable correct is to check how many predictions are correct, and total to count the number of samples in the test set. So in the test process, we don't need to backward process. So there is a little bit difference in code between the inference and the training. The test process don't have the backward or optimized process. So let's try to check the accuracy. So it says the 95% accurate. And compared to the previous model that has the one linear layer, the accuracy is a little bit higher. So this is the end of the code for the practice session, and you can change all of the parameters or hyperparameters or the structures of the neural network and try it by yourself. So now on, if you have any question, please feel free to ask me, or you can just ask on the KLMS Q&A section. One student asked us that the PyTorch tensor seems to include all the function of NumPy. So why we use NumPy? So yes, you're correct that PyTorch tensor and NumPy arrays are very similar in functionality. And the PyTorch tensor include most of the same operation as NumPy. But however, the difference between them is that PyTorch tensor can be unloaded on the GPU for the faster computation. But the NumPy array is for more general purpose, and actually it was used for like scientific computing, not for deep learning in the past. So which means that NumPy is more suited for the general purpose, like scientific or computation. But when we try to use the GPU accelerated computation, we need to use the PyTorch. And another student asked me that in this code model neural net, I think here. So one student asked that, this code, is it basically means that there is only one hidden layer, right? How do you write the code if you have, let's say, 5 hidden layers? So in this example, it has 3 layers, like fully connected layer 1 and FC2, FC3. So it has 3 layers. And when we define the model like this, neural net, we need the variable for the input size and hidden size and output size. And we use the same hidden size in all 3 hidden layers. So we just use the we only set this parameter only one time. It doesn't mean that the one hidden layer, because the hidden here the input size is 784 and hidden size 20. Again, the FC2 layer has the input hidden size of 20 and then output hidden size to be 20. And the FC3 layer has the input hidden size as 20 and then output size should be 10. So it has 3 layers. So if you want the 5 hidden layers, you should give 5 different layers in the model structure. And another student answered that NumPy is for CPU and PyTorch is for GPU. Yes, it is right. Another student asked me that, not related to this class, but my AI504 chatbot has been saying this app has encountered an error since a few days ago. Does anyone else have this? Students who are suffering from this problem, please use the KLMS, the Q&A section. Then we will check those students' AI chatbot. Okay, several students are suffering from this problem, so we will check it. And another student asked that, so if we want to know the number of hidden layers used, we need to look out for the number of self FC. Yes, you can see, here, like this, self FC, FC1, FC2, FC3. So it has 3 layers in here. And actually, when you want to check the structure of the model, after you define the model, you can print it like this. Here, the model name is just model, so we can check the structure like this. And it shows the structure like this. And another student asked that, what is the difference between total step and mini batch when training the model? So, total step is, in this example, mini batch is the batch that is used for each step. So here, the mini batch, it has the batch size of 128. So which means that 128 samples from the training set are used to train one step. And total step means that all of these steps, like we set the epoch as 10, and each epoch has the 4 steps, so it has 40 steps as total step. And another student asked that, in this code explaining simple linear operation, it says linear function is simply wx plus b, and the result from the matrix 1 to 3 result in 0.6186. I guess it's because of the implicit weight values and bias value. How do we know the default weight values and bias values? Okay, maybe the code is so here we define the linear model, and the input size is 3 and output size is 1, and this linear function means the wx plus weight matrix multiplication of the input x plus bias. So when we try to check the default parameters of the weight and the bias, we can check like this. After we define the model, so this is the model, and when you try to check the weight, we can print it like just weight. So it says the setting of the weight, and when you try to check the bias used in this computation, you can check it like this using the bias. Okay, is there someone has any more question? Okay, then I will wrap up the practice session. If you have any more, oh, okay, here is one more question. The epoch is dataset, so which in this case is 60,000. Step means each step is basically a mini batch data of 120. Yes, one epoch means the training step passes all of the data set, and each step is basically a mini batch data of 128. Yes, it is right. Okay, I will stay 5 more minutes, and if you have no questions, you can leave the class now. And if you have any more questions, you can use the KLMS Q&A section. One student asked me that then each step is an image of the mini batch. no, each step is an image of the mini batch. Yes, in this example, we use the MNIST data set, which each sample is composed with 28 by 28 pixels of image and the label, which shows, which means the actual digit of the picture. And each step, it has composed of the 128 images. So the shape of the matrix might be 28 by 28. Oh, because it has the batch size is 128, the input matrix shape should be 128 by 28 by 28. But remember that when we give the input to the model, we reshape the model to flatten it. So we converted the 28 by 28 to the 784. So the input after this process, after we reshaping it, the input shape might be 128 by 784. Then what does the total step 469 mean? Where it is? 469. Is there the number like what 469? The number is in the log training block. Oh. You mean that here the step is 169. It means that for each epoch, in each epoch it passes all the data set, but it is decomposed with 4 mini batches. So because the mini batches are decomposed with the 4 steps in each epoch, and each epoch has. Oh wait, I'm a little bit confused. It means that in one epoch, it has to step 469 steps. And here, because we only print the every 120, 200, 300 steps, it gives this result. If we want to print all of the step in each epoch, we can print it like just print this loss and epoch for every loop of that, but we wrote the code just like this. It only shows the 100 and 200, 300, 400, all these passes. But it means that the epoch has 469 mini steps to finish one training. Yeah. I think there is no more questions, so I will wrap up the practice session. And if you have any more questions, please ask in the Canvas Q&A section. Okay, you can leave the classes now. One question asked me that images reshaping. I get that 28 by 28 is basically the size of each data point. Yes, but I'm not sure what basically -1 represents. Yes, when you use the reshape function here, like this, okay. Before it, when you try, let's see the shape. And after we reshape it, oh, wait. You mean this -1? Okay, this -1 just we don't need to like, for example, if the input size like 10 by 1, then if I want to make it if I want to convert the tensor shape like 5 by 2, then we only like this. Actually, it was like, and we want to convert it like 5.2, this shape, then we can call the function like this. Reshape like -1 and 2. Then it automatically sets the shape as 5 by 2. So we don't need to calculate if we set 2, then what is how many columns do we need or how many rows do we need? So we only need to set this column number, and then it automatically sets the row number as 5. So -1 means like that. Okay, now I will finish the session. If you have any more questions, please ask in the comments, and we will check the issues from using the AI chatbot. Okay, thank you. Bye bye, everyone.